In this video, we're going to talk about what determines a cell size and how we can model this mathematically. This is going to be our very first mathematical modeling of a real biological process, but we will use all the tools that we've built up so far, talking about power functions and their relationship between each other. So as for a little bit for motivation, let's first think about what physical and biological constraints determine the size of a cell. Why do such limitations even exist? And why should animals be made up of a million or millions of tiny little cells as opposed to being one giant cell, right? There must be some biological constraints because nature does not make haphazard decisions, and we're going to try to figure out what they could be. So first of all, we're going to have to make some assumptions on the shape of our cell. Because this is our very first example, we're going to assume the simplest shape but rather common one among cells. We're going to assume that our cell is going to be spherical. Okay, so a nice sphere. The model is gratitude to my wonderful student Noah. Papi shared that for me last year. We're going to assume the cell is spherical. Okay, this is very important because this also means that whatever conclusions we come up with will only hold for spherical cells. And you will see other types of cells and what that means in terms of their size on your homework and in class. The other assumptions we're going to make is in regards to absorption of nutrients and consumption of nutrients. So we're going to first of all assume that the cell absorbs nutrients through the surface as it interacts with the outside world. We're going to also then assume that the cell has to sustain life in its entirety, therefore it consumes nutrients proportional to its volume. Okay? So absorbs proportional to surface area, consumes proportional to the entirety of its volume. Now, this results in two interesting balancing ideas. On the one hand, the larger the surface area of the entire cell, the more nutrients it can absorb, right? But then, if you increase the surface area, you also increase the volume, and therefore you need more nutrients to actually sustain life. Okay? And this interesting balance is exactly what determines how big a cell of a certain shape can be. Let's think about all of these things mathematically and try to describe with formulas, especially now that we have a specific shape, what all of those things are. You will of course recognize that we're already talking about proportional things here and therefore are able to utilize the previous unit. Here are some variables that we're going to introduce. Because a sphere is fully determined by its radius, it is convenient to have r as the radius of our cell. S is going to be the surface area of the cell, and because it is a sphere, we actually know exactly what that is. The surface area of a sphere is 4 pi r squared. V is going to be the volume of the actual cell, and again, because it's a sphere, we know what that is in terms of our radius, 4/3 pi r cubed. Now we need to think about nutrients being absorbed and nutrients being consumed. So for shorthand, we're gonna let A be the absorption rate per unit time, whatever fixed amount of time you want to think about, and C is going to be the consumption rate that is necessary for the cell to survive per same amount of unit time. And now, in order for a cell to live, it needs to essentially take in more food than it needs to sustain life. So what we want is that our absorption rate is at least as large as the consumption rate. Okay? If the absorption rate falls below a certain threshold, the cell cannot absorb enough nutrients to actually feed itself and it will die. Okay? With this in mind, we're going to see how we can model these processes. You will also recognize that now that we are down to specific functions, all we're dealing with, the 4 pi and 4/3 pi, are constants. So we're looking at something times r squared and something times r cubed. And those two are power functions. So hopefully we'll be able to use our analysis from before to apply to these. Okay, let's go back through the assumptions and see what that means with regards to our newly introduced variables or using our newly introduced variables. So the cell is spherical means that we actually have the formulas for surface area and volume in terms of the radius. The next assumption was the rate at which nutrients are absorbed is proportional to the surface area of the cell. So the rate at which the nutrients are absorbed is A, denoted by A, and it's proportional, remember our little proportion sign, to the surface area of the cell. Okay, or A is proportional to S because that's what we called it. Remember that proportional means that it's actually equal to some constant, let's call it K1, because we're also going to need a second constant later, times the surface area, S. And we also know the surface area of the sphere in terms of its radius, and we would like to minimize the amount of variables that we use throughout. So what this implies is that A is K1 times the surface area of the sphere, which was 4 pi r squared. Excellent. We're going to do something very similar for the volume. In fact, you might want to take a minute and try the volume part for yourself because it is completely analogous to the surface area argument that we've just made. The rate at which the nutrients are consumed, so the consumption rate that we denoted by C, is proportional to the volume of the cell. Okay, so let me just write down volume that we denoted by V. This again means that I have C is equal to some constant, let me call it K2 here. It's some constant, some positive constant, times the volume. And once again, because it's a sphere and I know what the volume is, I can rewrite this fully in terms of the cell's radius. Okay, so here K1 and K2 are positive constants. So let me just make sure that we're on the same page with that, a positive constants. And in order for the cell to survive, once again, we just need that the absorption is greater or equal than consumption. But now we can write that out not in terms of A and C, but rather in terms of the formulas for them that only have the variable R, and everything else is in fact a constant. Okay, so let's do this here. So what I want is that the absorption is greater or equal than consumption. Oops. From the last slide, my absorption was K1 times 4 pi r squared. And I would like that to be greater or equal than consumption, which from the last slide was K2 times 4/3 pi r cubed. Okay, let's reshuffle things a little bit. Once again, thinking back to where all of these numbers came from, K1 is a constant and K2 is a constant. Pi is a constant here and there, and then 4 and 4/3 are obviously constants. So I'm going to essentially introduce brackets so that the two pieces are separate. So I have something times r squared, and it's greater or equal than K2 4/3 pi times r cubed, where this and this are both products of some constants. Now honestly, I don't really care what those constants are. All I care about here is that they are in fact constants, which means they're numbers, okay? So this is a constant, and this is a constant. Okay, so just to make it a bit easier on the eye, let's rewrite this expression and replace this bulky, lots of numbers and letters, which is just one big constant, with something a little more compact, okay? So let's say that this constant is some number, and then you notice that it's this number times r squared. So I have number times r squared greater or equal, and then again, this is some other number times r cubed. Okay, so now all I see is that I need to compare a power function with r squared versus a power function with r cubed. So this actually just boils down to comparing 2 power functions. And this we already know how to do. Okay, so let's sketch ourselves a little graph here, because graphically this information is actually a little bit easier to parse. So what I have is two axes. This is going to be my r-axis, okay? And what I need to sketch here is this that corresponds to, remember where it came from, this corresponds to absorption. So in fact, maybe let's label this too. So this side corresponds to absorption, and this side corresponds to consumption. Okay, so let's sketch this one. In terms of r, it's r squared times some number, but again, remember our discussion about power functions, it's some number times r squared. The power is the one that dictates the overall shape, and then the coefficient in front of it simply makes that shape narrow and taller or wider and shallower. R squared, the shape, is a parabola. So let's draw our absorption here as a parabola. Okay, so let me try to make it as pretty as I can. Okay, that's not too bad. Okay, and let me label it right away so that I don't forget that this is in fact absorption. Okay, and for the other graph, for the consumption, what I have is that it's some number times r cubed, which again means that it's the general cubic snaky shape times some number, so it might be a little bit stretched out or flattened out, but the overall shape is a cubic function. And then here is what we practiced before with sketching two power functions on the same graph. Recall that this is the square power, and this coming in here is a cubic power. For small, near the origin, for small values, the smaller powers dominate, which means that near the origin, my cubic function has to lie below my parabola, and then far away from the origin, it will surpass it. Okay, let me make it a little bit prettier here. Oh boy. There we go. Something like this, okay? Let's pretend that this is nice and smooth. And this is for consumption. From our analysis of the power functions before, we know that these guys will intersect again at some point, but let's analyze what happens before and after that point of intersection, that switch in this case. Okay, so let's take a look at this here. Remember that the purple graph corresponds to absorption, and then the blue graph corresponds to consumption. So before this switch point here, I can see that absorption is above consumption, which means that the cell can absorb more nutrients that it needs to actually consume, right? So on this, we can split this up, right? So on this first region, absorption is bigger than consumption. And then after this point, we see that the consumption dominates absorption. So afterwards, the consumption is going to be bigger than absorption. And you can analyze it using numbers. So I strongly encourage you to actually plug in some numbers into these two expressions and make sure that you see that for small values of r, the r squared will give you a higher value, whereas for large values of r cubed is going to give you a much bigger number. Okay, but so we start off by wanting A to be greater or equal than C because we want the cell to have more nutrients available than it needs to eat. And we can see that it is actually on this region that it happens, right? This region is where the consumption lies below the absorption, which is exactly when the cell is going to survive. Once we are past this switch point, the consumption lies on top of absorption, which means that now the cell needs more nutrients that it can actually take in, which unfortunately for the cell, it means that the cell will starve. There's just not enough nutrients, right? So here we've determined that essentially this is what happens. For small values of r, remember this is our r-axis, for small values of r, a cell is able to survive, and then it will reach a certain point in its radius, which determines its size, where the consumption, the nutrients needed to sustain life within a large spherical ball will be bigger than it can absorb through its surface area. Okay, so it's kind of like past a certain point, the surface area grows slower than the volume. And that's key here. This is exactly why spherical cells are all going to be fairly small, because this threshold will occur in terms of radius, and once they hit a fairly large radius, they just won't be able to sustain life. Okay? Now, as I emphasized in the beginning, it is extremely important to realize that your assumptions guide your conclusions. Our assumptions, one of the first assumption was the fact that the cell is spherical, which means that our conclusions only hold for spherical cells, something that looks like this. Isn't this a great model? This also means that if you encounter any other shapes of cells, your conclusions might not hold for them because your assumptions are not the same for this case. So let's think about what are some of the most sort of notable exceptions to this conclusion for spherical cells. Actually, this, first of all, is just a little bit of how big different kinds of cells are. So, for example, we see, in general, the measurements are fairly small, but in general, they go from something very small to something a little bit bigger. But also notice that as we move along, we might start off with cells that are at least spherical in part, like the various viruses are spherical. We should know a lot about the shape of coronavirus nowadays. It's all over the news in the actual pictures, right? And then as we move further and further away, so some cells keep the sort of spherical cell shape, but some cells become way more complicated, right? So if you are to be bigger as a cell, you seem to need more complicated structure, or most definitely not perfectly spherical. So let's take a look at some exceptions. Neurons. Neurons are giant cells that actually span much bigger sizes than what's in this table, right? But that is, of course, because they're far from spherical. The nucleus is spherical, but everything else is just a really long, skinny, cylindrical piece. Things that are flat, like, for example, seaweed cells, these are all one-cell organisms. They're flat, but quite long, right? Which allows them to keep their volume very, very small, but their surface area is very large. A variety of plant and animal cells are not as simple as the cell that we've talked about, and that's because we also made this sort of hidden assumption that the cell is made up of all the same material inside. Whereas, for example, plant cells actually keep water inside of them, so they keep a part of their nutrient reservoir inside, and they don't purely rely on absorbing from the outside, which was one of our assumptions. Along the same logic is the egg, right? It keeps everything that it needs to survive inside of it, except for the oxygen that it actually gets through the highly permeable shell. So these are some of the conclusions. If you're a cell and you would like to be three-dimensional, the best bet is something like a neuron, which is long and skinny, so keeping the volume down while increasing your surface area, or filaments or sheets, which are very flat, so very small in volume, but very, very big in surface area. And then essentially, in order to be big, you have to be breaking one of the assumptions that we made from the beginning. Don't consume proportional to volume, or maybe have reservoir of food inside, or play with the constants of proportionality and make one a lot bigger than the other, and then you'll be able to sort of move that point of intersection further to the other side. And again, to emphasize, predictions of any model are only as good as their assumptions. So if you've assumed yourself is spherical, your conclusions will only hold for a cell that is in fact spherical. As an example of almost the opposite way to model things, let's take a look at Bergmans Room, which is a zoological principle that relates external temperature to the size of the body of the animal that lives in that climate. Now, as opposed to the mathematical way of modeling, where you state your assumptions and then draw out your conclusions, in some natural sciences, a lot of conclusions are first formulated based on observation and then somehow supported by logic. So we've witnessed the fact that, so let's take a look at our conclusion here first. we can actually observe in the real world that the species of the larger size are found in colder environments, whereas the species of the smaller size are found in warmer regions. And in the attempt to actually explain why this happens physiologically, zoologists came up with the following justification. Larger animals have lower surface area to volume ratio, so they radiate less body heat, whereas smaller animals have the exact opposite relationship between the surface area and volume, and therefore need to be able to dissipate the heat quickly. Again, this is not a proven. Real animals are much more difficult to model rather than nice spherical cells. And so these types of conclusions or these types of principles, watch out, they are not really proven. They're just empirical in the sense of this is what we've observed, but we've observed it enough times to seem that there is some kind of underlying principle to support our conclusion. But let's take a look at some of the observations and see why it's tempting to make such a conclusion even without the mathematical support. So for example, polar bears. Notice the difference in size is fairly striking. Polar bears are in size between 350 and 700 kilograms versus a brown bear that actually lives in BC that starts off at a fairly small 80 compared to the polar bears, 350. Hares or bunnies. Our bunnies here are, again, fairly small. I can see some outside of my window at my U of V office right now actually running around. Whereas an Arctic hare is just a much larger animal. And so again, this kind of goes together with the colder the environment, the bigger the animal in it. And then of course there's snow people. Canadian snow people are much larger than a Brazilian snow person can ever be.